Welcome everyone. In this video, I will be covering section 15.3 double integrals in polar coordinates. Earlier two sections were about double integrals over rectangles and double integral over general region. And this section is about double integral using polar coordinates. Sometimes converting rectangular coordinates to polar coordinates is make the problem or make the evaluation of the integral very simple. So sometimes a double integral is easier to evaluate using polar coordinates. This is especially true if the region of integration can be easily defined using a polar equation. The following formula is often used to convert rectangular or Cartesian to polar coordinates. If you look at this picture where you have both polar coordinates and rectangular coordinates are x comma y, and then polar coordinates are r and theta. We are keeping this the point P in the standard position. So you have a right triangle. The adjacent side is x, and the opposite side of theta is y, and then the hypotenuse is r. So using Pythagorean um, theorem, we get r square equal to x square plus y square. And we know that cosine theta from this right triangle is adjacent over hypotenuse. So x would be equal to r times cosine theta. And then sine theta is opposite over hypotenuse. So y equal to r times sine theta. So x equal to r cosine theta, y equal to r sine theta. Change to polar coordinates in a double integral. If f is continuous on a polar rectangle or where 0 less than or equal to a less than or equal to r less than or equal to b, which means r basically lies between a and b, and theta lies between alpha and beta as shown in this picture. So from the origin to this position, the distance is r. From the origin to this position, it will be dr more. That will be b. So r lies between a and b, and the distance between them is dr. So if you consider this polar rectangle, it is equivalent to, it's approximately equivalent to a regular rectangle. Here, the area of this polar rectangle can be approximated by the regular rectangle, which is length times width. The width is the distance between A and B, which is dr. The length, if especially this part, can be considered as the length of an arc. It is the length of an arc. That will be radius times theta. Radius times the angle that it subtends. So radius in this case is r. Then the angle that it subtends, so instead of writing theta, we would write angle. Angle that it subtends the angle that this polar rectangle subtends is d theta. So the length in this particular case is r times d theta. So length can be replaced by r times d theta. So the area of the polar rectangle, so area of the polar rectangle is r dr d theta. So this area here is r dr d theta. So double integral over R f of x y dA can be written as double integral, one for theta, which is alpha to beta, the other one for R, which is uh, from A to B. Then f of xy changes to f of x becomes r cosine theta, y becomes r sine theta in polar coordinates, and this dA is the polar area, area of the polar rectangle, which is equal to r dr d theta. The explanation for r dr d theta is given here. So it is the length times width of the polar rectangle. Length is r d theta and the width is dr, so it becomes r dr d theta. How do we change from rectangular coordinates to polar coordinates in a double integral? Why would you want to make that change? We want to make we want to change from rectangular to polar in a double integral if the region D of integration is more easily described in polar coordinates. So if D is r comma theta, where theta lies between alpha and beta, now r lies between h1 of theta to h2 of theta, then to evaluate double integral over d f of xy dA, what we do is we change them to polar the following way. It is from alpha to beta, that is the variations for theta, which are definite limits, whereas the variations for r would be one polar curve to another polar curve, which is from h1 of theta to h2 of theta, which you see here. And then f of xy, it is f of x is r cosine theta, y is r sine theta. Then you know that dA changes to r dr d theta in polar coordinates. Sometimes converting the problem to polar coordinates becomes very easy. The evaluation becomes very easy. Then I have done problem number 7, 15, 19, 25, and 29 in the videos for the section. Please refer to the videos for the section for these problems.